Today is going to be the last of our new material for the class. So we're going to be talking about thermal expansion, and then buckling. We'll review our basic elementary buckling theory and then apply that to some thermal expansion cases as well. So this will be our last regular class, last of the new material that we'll have in the class, which will line up with about a week from our last homework review. I try to give us at least a week between material covered and an exam. Wednesday, we're going to have a special presentation. For those of you who are joining remotely, I'm going to run it on Teams instead of on Zoom so I can talk the CUI stuff, and that'll be U.S. students only. For resident folks, they'll still just be in here in the same room. So you'll get a special invite in Outlook for that one for Wednesday's meeting. But if you're joining resident, then just come same. And then we'll have our homework review next Monday. A couple of you asked about an early version for that homework review to take tests a little early. That's fine. We'll work that out offline. And then general exam time going to be Wednesday, 10 June and following. Of course, if you're TDY or you have flight line hours that day, et cetera, we can be flexible at that time. Doesn't look like we're going to need any of week 12, so that can be all done with. All right, so we're planning on being finished with doing our last exam on next Wednesday. So let's go ahead and dive on over, talk about thermal expansion. This is going to be our 7.1 slide deck. So thermal expansion is a material-specific property, and it occurs in our volumetric directions. That is all three directions of X, Y, and Z. And it affects all three of those normal strengths. Does not have any direct effect on shear. Would somebody mind cutting the lights to about half power back there? I know it's a little bit light on coloration up on the screen. So our normal strain due to thermal expansion, epsilon thermal, is going to be alpha times delta T. And that's going to be added for epsilon XX, for epsilon YY, and for epsilon ZZ, in addition to the mechanical strains. Right? Alpha is a material-specific property, our coefficient of thermal expansion. And then our delta T is going to be a change in temperature from some ambient or point that we count as zero stress. All right? Usually that's going to be room temperature, something along in there. So total strain for our material then is going to be a combination of the mechanical strain. So for example, in our 1D, that was sigma over E, right? Or whatever Hooke's law gives us, if we have multi-axial stresses, that's our epsilon mechanical, right? As a function of stress and Young's modulus and Poisson ratio. And then we also are adding to that our thermal strength. Now, those coefficients of thermal expansion, they have different values for different materials. Typical for a couple of the basic metals that we use, steel around 6 times 10 to the minus 6, and for aluminum, maybe 13 times 10 to the minus 6. Anything in the range of 5 or 6 micro per delta F, and 12, 13, something in that ballpark for aluminum. Micro per F is going to be typical. If you want these per C, we just multiply them by 1.8. Because it's per delta F or delta C, we don't have to adjust any 0 point with those. All right, it's just a straight. So this will be, something around 11 to 12 in the per centigrade category. And this will be in the neighborhood of a 25-ish, 24, 25 per centigrade category. All right. So these numbers look pretty small. These alphas are in the 10 to the minus 6. Even if we have a delta T that's in the 100 of degrees, let's say 10 to the 2, we're still talking about fairly small numbers. Low 10 to the 3s, high 10 to the minus, low 10 to the minus 3, high 10 to the minus 4 numbers for about 100 degrees delta T. So the strain numbers still seem fairly low, but they can add up to very big stresses if we don't allow these expansions to happen. We'll take a look at an example of what happens. So here's our basic Hooke's law. Remember what we covered in chapter 2, slide sets. was this right here, right? We all remember that one from undergrad. And these are our relationships between stress and strain. All right, for the basic 1D case, we just had sigma xx over E was epsilon xx. We didn't have any other stresses. And that alpha delta T just gets tacked on to each one of those normal strains. Notice it also has an equal effect in all three directions. All right. Nothing changes on these shear definitions. That's why we say it doesn't have any direct effect on shear. Nothing gets added to those formulas. So let's think about our simplest case of an axial bar. Everything's 1D and it's loading. So here's going to be our Hooke's law with thermal expansion. Epsilon xx is 1 over E times sigma plus alpha delta T. Now, in our case with free ends, one end free, so I can have one fixed and one free, or both of them free. We can't generate any load when we've got one or both ends free, right? No load on at least one end, and there won't be any load in the middle either. So sigma xx in those cases, force per area, force is going to be 0, then stress is going to be 0. That means our strains are going to be solely made of the thermal variety and not the mechanical variety. So if we have a bar and we don't do anything to it, here's my strain. Strain times original length gives me my displacement. Right? Change in length per original is strain, so I move the original length up. So the displacement I would expect for a bar would be alpha times delta T times its length. The opposite bookend case of that is where we have both ends fixed. Now, in that case, my total strain is going to be 0, right? Change in length per original length. If I fix both ends, my bar cannot change length at all. It's stuck at its original length. So there's 0 change in length divided by original length gives me 0 for strain. But that's the total strain has to be 0. So I put 0 in on the left-hand side up there. So I'm going to have a 0 right here for my fixed end case. But my alpha delta T is still working, right? If I heat it up, I'm going to get a big plus number here, or a little plus number. That means this one is going to have to counter to keep this total strain at 0, and we'll get some compressive value over here, right? So if I solve this for sigma, I can see I've got 0, so I can move this over to the other side and then multiply through by E. I get minus of E times alpha times delta T. We said I was going to have to come out compressive or negative mechanical strain to even out with the positive thermal strain and make the whole thing 0. No change in. Now, before this started looking pretty small. Alpha, we had 10 to the -6 range. Delta T, let's just say it's 100 degrees to make it simple. We got a 10 to the 2 range right there. So 10 to the -4, but modulus, all right? Modulus for steel and aluminum is in the 10 to the +7 if we're in US units, all right? We might have about 10 million PSI for aluminum or 30 million PSI for steel. So this is in the 10 to the 7th range. And then don't forget this alpha might have, between 5 and 6 and 12, something like that. So we're in some digit there. And then Young's modulus might also have 3 in front of that 10 to the 7th or something. So we could have even one more 10 to the 1st on top of this, depending on the units. But that's 10 to the 1. We're already in 10 to the 3rd territory and pushing up toward 10 to the 4th. If this alpha is 6 times 10 to the -6, and I've got steel at 3, well, 6 by 3 is 18. That moves me one more decimal place. Or if I've got aluminum, I got 1 here, but I got 12 there. So the product of E and alpha will probably give me another 10 to the 1st out here, just from the numbers in front of those. So now I'm looking at 8, 10 to the 4th for my stress units. That's 10,000 psi or 10 ksi, that's getting up in a really big stress range. A lot of basic materials might be 30,000 psi for yield, 36,000 for base steel. The softer aluminums are 30 to 40,000 as well. So I can get up in the same decimal place as the yield stress just from thermal expansion if I fully constrain those ends. So what looked like really small number here for alpha, and then we add delta T, but once we add multiply modulus on there, it starts getting to be a pretty significant number. So let's take a look at an example. Typical solar heating that we might see of delta of 100 degrees. All right. So it doesn't sound like a whole lot. We've got our two numbers for steel and for aluminum right there. And we crunch through and see what these values do come out to be. So we got minus E, alpha, and delta T. We saw that from the previous page. Well, let's give these a chug and see what kind of numbers we end up with. So for steel, we got an alpha of 6 times 10 to the negative 6 per F. Our delta T in both cases is going to be 100 degrees. And then we got our modulus, 30 times 10 to the 6 PSI. On the aluminum side, I got an alpha that's going to be a little bit higher. I've got 13 times 10 to the negative 6 and modulus of 10 times 10 to the plus 6. So 13 times 10 to the negative 6 per degree changed, and modulus for that one, 10 times 10 to the 6 PS. So sigma for steel, if I plug in all my numbers here, I got 30 times 10 to the 6 PSI. I've got 6 times 10 to the negative 6 per F. And then I got 100 F for my delta T. So the 10 to the 6 and the 10 to the minus 6, we can cancel that one off. I get 180 here and then another 100. So 180 plus 2 zeros be minus 18,000 PSI or 18 KSI. Remember, for mild steel like this, my sigma yield is 36 KSI. So I'm already halfway to yielding the material just by constraining a bar. And note that the length of this didn't matter, all right? My strains change in length per length. So if we're setting that strain equals here, it doesn't matter if it's the length of a long bridge or if it's a part of an engine block that's constrained or anything else like that. Regardless of our total length, based on the material, if all of it changes by that temperature, this is what we're looking at, 18,000 PSI of compressive stress. That's a really high stress, half as much as it takes to yield the material, just because we didn't allow any expansion. Now let's take a look on the aluminum one. Got a smaller modulus, so that's working for us. But we got a bigger expansion coefficient, that's working against us. 13 times 10 to the minus 6 per temperature. And then I also got that 100 degrees temperature change. So I got 130, add 2 zeros to it, I get 13,000 PSI for the aluminum one, or 13 KSI. And for soft aluminum, that's untreated aluminum. You might be up close to half of that yield stress. It's probably about a third of the yield for some of the tempered and heat-treated aluminums. But these are really big numbers from just a small temperature change. And it's not difficult at all to change an object's temperature by 100 degrees. A ship deck from 6 a.m. in the morning until afternoon on an equatorial climate can easily go up by more than 100 degrees in temperature change just from the solar heating of the sun. And then remember, we've got that dark, low observable non-skid on there that absorbs more radiant heat from the sun as well. So 100 degrees is Very easy to achieve for a metallic structure change in temperature. And we can see what happens when we've got constraints around on a ship. Lots of rigid constraints because the ship has a lot of structure around it. Also, highway bridges are important for this reason. So we can see how much stress they would build up. If we add the loads of the cars and the weight of the bridge itself and all those bending stresses, we can easily overload a bridge. That's why when we're driving across bridge sections, we're often going to see some kind of expansion joints. They'll often look like this, something like a form of teeth interlocking like this, and then some little gap in the roadway right here. So as we're driving over it and our tire rolls over, we go from one section of bridge, it's thump, 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 thump. If we drive over that bridge in the summertime and all these expansions happen, then the little grooves here will close up. That little gap will go down, and we'll hear a really soft thumping in the summertime as we drive over. If we drive over that same bridge in the wintertime, opposite thing happens. The bridge contracts, each of these sections shrinks, and with these expansion joints, that means the teeth are going to get farther apart, this gap's going to get bigger, and we'll hear a louder thump, 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 thump as we drive over that same bridge in the wintertime, because each of those sections of the bridge is shrinking in the cold or expanding in the heat. Now, if we put these expansion joints in there, we go back to the free end case. We won't build up any of these stresses, and then we're going to be okay as far as the loads. We only have to worry about the weight of the vehicles and the bridge itself and things like that. But if we were to build a single span bridge between, say, two earth abutments, like an arch bridge, and we don't provide any expansion relief, we can build up some really big stresses. This is also true with any time we put dissimilar metals together, right? If I've got a steel engine block and aluminum headers or vice versa, a lot of times nowadays engines are made of multiple materials. Well, we get that same kind of stress buildup. They may not be zero expansion, but if I bolt together a piece of steel and a piece of aluminum and I heat them both up, they're going to want to contract or expand different amounts. So we'll look at that next. What happens when we put two dissimilar materials next to each other? So let's think about two pieces that are attached to each other. So this could be bolts on the ends, they could be welded together, they can have some other method that they're affixed, but they're going to stay together. All right, so some kind of fastener on each end. This could be aluminum header and a steel block, or vice versa on an engine, also would count like this. But we're going to assume that they get heated about the same amount. All right, so we'll say delta T is 100 on both. Now, in the case of things like engines, oftentimes you're going to have one material that gets heated more, say the block, and then the header is going to be heated up less. So they may have different delta T's and different expansion values. Here we're going to think about the simplest case we can, same delta T, but different materials, right? And for simplicity, we'll make the area just 1 on both. And then we're going to have our modulus for both, same expansion coefficients as we had on the previous page, and we'll do a length of about 10. So we've got a 2-bar system like this. What we're primarily after first is what the loads are in each one, okay? So we've got some bolt or attachment that's affixed through one end of it, and then some kind of fastener attached through the other end. And it guarantees that they're going to either expand the same amount or contract the same. Now, the loads that are inside each one can be different, but the total displacement and therefore the total strength are going to have to be the same. So we might represent it by one end hatch. That'll be our reference end that doesn't move, and then the right side where they'll move the same amount. So that's to say that our U for the steel, our displacement, and our displacement for the aluminum are going to have to be equal. They've got to go the exact same distance, however far they go. So this is a 2-bar linkage. It's a classical type setup. So I've got the steel bar or the number 1 bar, the aluminum bar down here. This works for any 2 pieces, doesn't matter what you call them, steel, aluminum, 1, 2, A, B, etc., etc. So U for the steel and U for the aluminum go the exact same distance. That means however much this one stretches, this one's going to stretch by the same amount. So there's my primary boundary condition. U for the steel equals U for the aluminum. That's our displacement. Now, the other thing that we've got to work with is the forces. There's got to be a balance of forces in the system. So let's take a slice on one end. Doesn't matter which end we slice. Since this is kind of our free end, I'm going to take a cut on that side. We can visualize it as simply as possible. So if I just take a slice off the end there, and remember for my axial bars, my force is a positive tensile. So we just draw it out of whatever surface we just cut. Summation of forces equals 0. These are both going the same way. So F steel plus F aluminum have to add up to 0. Whether I call it minus F steel minus F aluminum, or we add them up positive this way or positive this way, they're on the same side. Right? They're both pushing the same direction. So what this tells me is in any kind of a 2-bar setup, one is going to have to equal the negative of the other. Or F aluminum equals minus of F steel. They got to have an equal and opposite force because the only thing supporting them is each other. So this will let me plug in one for the other, and then I have an expression for displacement. Remember, displacement I can say was strain times the original length. And over here, strain for the aluminum, original length for the aluminum. So displacement, I can do strain, which is displacement per original length, and then times the original length will get me displacement. And this is where we've already made up the formulas for epsilon. So let's take a look at what those formulas will work out to be. So I had for epsilon sigma over E plus alpha delta T. And for displacement, I could do epsilon times length. So it's going to be sigma L over E plus alpha delta T and L. And then for sigma, my stress is force per area. All right. So I can substitute that in there. And now I could say my displacement for either one of those is going to be FL over AE plus alpha delta TL. So we've got U steel equals U for aluminum. That's going to be force steel, area for the steel, E for the steel, plus alpha. Basically everything with a steel subscript equals everything with an aluminum subscript. Area for the aluminum, E for the aluminum, and alpha delta T. Now in the 2-bar linkage, the way we have it drawn, the lengths are going to be the same. So I can see the lengths can fall off, and that also means that it's true when we've got 2 bars that are the same length, as in this setup, that epsilon for steel equals epsilon. Could divide that length out. We also have a same delta T in this case. So let's plug in our specifics. We got a delta T equals just the same of 100. And then I got a length. That just means I can cross those off. All right, so those can go and those can go. We'll drop one. Now, the other thing that we have working for us is that I've got F aluminum equals minus F of steel or vice versa. All right, so I can plug in for the other one right here. All right, we can cross through and put that one in. So I got F steel, L over AE, all with the steel on there. I got an alpha. And then over here, I'd have the minus of F steel. I'm going to leave those subscripts on for just a second so we can see a full expression. Delta T, aluminum, and length. So if we were to solve this one just for F steel, I can move this one over here. I can move this one over here. I'm going to get F steel times L over AE, all for steel, plus this stuff, L over AE, all for aluminum. And then on the other side, I'm going to get my alpha aluminum minus alpha for steel. We've got the same delta T there and that same length there. So if we clean up and make an expression here for our specific case, let's see what it comes out to be. Force in the steel is going to be alpha aluminum minus alpha steel delta T. We can cross off the L's on the top and bottom if we like, or we can leave them there. And then I've got L, A for the steel, E for the steel, plus L, A for the aluminum, E for the. So here's my expression. Now I can see that alpha for aluminum is bigger than alpha for steel. So that one, for this case, if we're solving for steel, this should come out as a plus. And do a positive delta T. Length has to be positive. And then everything down here, we can't have a material if there's negative area or negative modulus or negative length. So everything in here comes to a plus sign. That means my steel should be a tensile number. And remember F aluminum minus F of steel. So that one will have to come out as a negative number. So regardless of how much my delta T is, as long as it's a positive number, I'm going to stretch the steel in tension and I'm going to compress the aluminum. So let's think about what those two look like. Let's do red for the steel and we'll do blue for the aluminum piece. So my original setup, I have the aluminum down here. I'm going to make an original length where they're the same. And my steel bar right next to it. They're both L long to start. Now I heat up the steel, and it does want to expand. It wants to go maybe this far. Okay, we'll exaggerate a little bit, but say it goes about that far. If I heat up the aluminum by the same delta T, I know it has a higher alpha. So if it weren't attached to the steel, it might end up out here. Okay. This one's going to expand more, the aluminum one. And the steel one's going to still expand, but less. So if I force them to stay together, that end piece or bolt or fastener or whatever I've got is somewhere in between where this red one and blue one showed up. If I'm going to force them to go the exact same distance, U for aluminum, U for steel have to be the same, then beyond where it would go by itself, I've got to stretch the steel one out. See, I get a positive or tensile value there. And I've got to push back on the aluminum one. I've got to push it back to meet where the steel. So I've got to pull out on the steel. I got to push in on the aluminum. And they're stuck together somewhere in between those two spots. But the one that would have expanded more, I've got to compress it. The one that would have expanded less, I've got to stretch it to meet them at the same spot. And that's what our formula shows us here, is that for everything in here with a plus sign, alpha for aluminum wants to expand more. There's a bigger number than this one. So this is a plus, delta T is a plus, L is a plus, and everything on the bottom's got to be plus. So that shows me that my steel had to be in tension. And if I just drew it out visually, that's also what I would expect. Tension for the steel and compression for the aluminum. And they're equal and opposite, so they have to be the same amount. All right, does anybody have any questions about that 2-bar linkage there? All right, so that's probably among our simplest setups where we've got same delta T for both. And we showed that the one that wants to expand less is going to be in tension. The one that would have expanded more on its own is going to end up in compression. All right, let's jump over and think about a little bit more complex bar structure. So here we're going to have 3 bars in our linkage. We got 1 and 2 back to back, and then we've got 3 in parallel to that. Now let's say we want to solve for all 3 of our forces, right? That means we're going to need 3 equations from a combination of our free body diagrams and from our displacement equation. So let's talk about the free bodies first. Should be some empty space on the next page, but I'll scribble a little bit on here. So first thing first, for the free bodies, I can still do what I did before and cut the end. So I get a relationship between 2 and 3. And then when we've got multiple bodies like this in a row, what we want to do is cut at that intermediate spot. So this is another spot right here we can check. So let's see how those work out if we cut those free bodies on paper. So here I've got bar number 1, bar number 2. They're back to back, so they're in series. And then in parallel, I've got bar number 3. So they're going to be stuck together on the front and the back end. My free body where I cut in the center there, I got 2 here, I got 1 here. Well, I got F1 coming out there, I got F2 coming out this way. So that tells me, and it's probably pretty intuitive to guess, that F1 and F2 should share the same load. There's nothing intermediate between those two. So the load's going to have to pass straight through 1 and same load on number. All right. So that gets us one relationship. And then I can also take a slice on the end. So I've got F2 at the top. I got F3 down at the bottom. So this is another free body on the end. This one's somewhere in the intermediate region where 1 and 2 meet. And here I got 2 and I got 3. So this one, if I sum up forces, I could see that F2 is going to equal minus of F3. So now I've got relationships between 2 and 3 and 1 and 2. Or I could also sub in and say that F1 equals minus F3, either one. But this is 2 separate equations that I have to work with. So I can hop down here, but I have 2 independent equations that I have to work with. That means I need one more. The other one I can get is from the displacements. U on the top piece and U on the bottom piece are still going to be equal like they were before. So down here, I've just got U3. On the top, I've got to add the displacement of 1 and the displacement of 2. So U1 plus U2 is going to be on the top. And these are what we have to equal out with each other. So then my boundary condition is going to be U1 plus U2 equal to U for the third piece. Same thing as we had before. I got FL over AE for 1 plus alpha delta TL for 1 plus same stuff for 2. And then all that's going to equal that stuff for 3. And I'm putting the parentheses here. I'm just applying the subscript to all of them. Now, in this case, we can't cancel L through like we did before because length 1, length 2, and length 3 are going to be different. But we do still have our force relationships, right? So we can solve for a single force now. I've got 1 in terms of 2, I've got 2 in terms of 3, I've got 1 in terms of 3. So I can substitute any 2 of these forces in with the third one, and then we can solve for the third one that we're looking at. So why don't we jump in and solve for number 3, and we'll see how that works out. All right. So we'll keep F3 in here for F2. I'm going to put in a negative, or for F2, I'm going to put in a negative F3. And then I can also see that 1 equals 2, so I can put in a negative F3 over here as well. So F1 is going to go to minus F3, F2 is going to go to minus F3, and that's going to leave me with just forces number 3. All right, so I can gather all those together. On one side, they're going to all go together. So I got alpha delta TL for 1 plus alpha delta TL for 2. And then I'll move the third one over here, alpha delta TL for 3. All right. Put the thermal stuff on one side, and let's put all the forces on the other side. So I've got F3. I got L over AE for 3. And then because these have a minus, when they come over here, they'll become positive as well. L over AE for 2 and L over AE for 1. So if we get a final expression here for F3, it's going to be this stuff on the top. Alpha delta TL 1 plus alpha delta TL for 2 minus alpha delta TL for 3. And then on the bottom, I've got all those L over AEs. Now on the bottom, is there anything that we could possibly get negative? No, everything, L, A, and E. This is guaranteed to be a positive on the bottom, right? So the numerator is just some multiplier. We're not going to worry too much about that. That means what controls whether we go into tension or compression is going to be solely based on these alpha delta T combinations that we got up there. Remember, length can't go negative and alpha can't go. So it's really the delta T's that are going to control what goes positive and negative, and they're multiple on those alphas. All right. Alpha as a numbers, always going to be positive. L as a numbers, always going to be positive. So these products are going to be plus or minus based on the delta T's individually, and they're going to depend on those product values. So let's think about just a couple of bookend cases and see how it works out if we think it should be this way or not. So here's our 3-bar linkage. Let's say we heated up just number 1. Okay. I'll move this up to the top. All right. I delta T just for number 1. All right. We don't heat up number 2 or number 3. If I heat up number 1, it should be expanding out. Number 2 is going along for a rigid displacement, and number 3 not moving at all. So in between those two, I'm somewhere right here. I should have to push back on this top column and pull out on this bottom column to meet them together. And that's what this formula tells me. If I have just delta T1, I get a positive number in the top. And that means F3 is going to be, as a formula, is going to be tension. And because F2 and F1 are just the negative of this, then that one would have to go in compression. So that passes the test okay. I could see also if I heated up number 2 by itself, same deal. Let's say we just heated up bar number 3. So if I just heat up bar number 3 here, then I know that third bar would like to stretch, but 1 and 2 aren't going to move at all. So I'd have to push back on bar number 3 and pull out on bar 1 and 2. And that what tells me if I only have a delta T3, I get a negative or compressive on that bar number 3. Now, in a real world type situation where we might have lots of components together in an assembly of an engine, maybe they're all going to get different delta T's. All right. Now, if it was the same material, we heat up 1, 2, and 3 and say it's all steel, what happens? Well, the force is going to go out to 0. These will stretch by a certain amount. This will stretch by the same amount as both of those together. So if I have the same alpha and the same delta T, it comes down to L1 plus L2 minus L3. And L1 plus L2 equals L3. Right? So same material, same delta T, we wouldn't have any stresses or forces built up. But in an actual assembly, what we'll probably have is, say piece 1 and 2 are heated by a different amount than piece number 3, and they're also a different material. But this formula will give us what we need, no matter how many pieces we have. If there's 3 on the top and 2 on the bottom, it would fill in a little bit more. But we can always tell the basic pluses or minuses whether they work out by looking at the simple case. If I heat up 1 or I heat up 2, I'm going to get a positive for F3. That's this top picture. If I just heat up number 3, I see there's a big minus sign on that one in the numerator. So if I try to expand number 3 and 1 and 2 are hanging on, we're going to have to push back on them. So that shows us a little more complex case, but I can see that it all comes out passing the sanity check there. Anybody have any questions about how we set up that multi-bar linkage there? All right, so let's talk a little bit about non-uniform thermal expansion. Now, in all these prior examples, we assumed that delta T was going to be a constant on each of those bars. So for uniform thermal expansion, epsilon's alpha delta T, and delta T was a constant. Then when I integrate up to displacement, it's just alpha delta T times L, because everything inside alpha and delta T were constant. But very often in real life, our distribution is going to be something non-uniform. So that means my delta T might be a function of my position down the length of that bar. So epsilon thermal is still going to be the same equation, alpha delta T, but now it's a delta T of X. All right. When we're going up to displacement, what we're really doing is we're saying integral of epsilon from 0 to some position. All right. So my epsilon is going to be F over AE plus alpha delta T, and delta T is just going to be a function of X. So this time, both of these can't just hop out and we get integral dx, which gives us our 0 to L or just times L. We're left with this delta T inside the integral. All right, so alpha can still come out. F over AE should be a constant along the bar. Force is a constant. We still get FL over AE, but now we've got alpha and integral delta T dx over the length of the bar. Even if we have a delta T that varies all down the length of the bar, the ends are still where our force is applied to the bar. So same force regardless of what the delta T distribution is. That's an important part, is that F over AE still comes out as a constant. So this becomes the displacement due to thermal expansion, and we see that can vary based on the shape of delta T. So let's take a look at an example here. Here, our delta T of X is going to go from some high temperature down to room temperature or base temperature on the right side. So if on the left side, I've heated it up by T naught, that's how much my delta T is on the left, and my delta T on the right is 0. This might be something like we see in the case of a turbine where we got hot exhaust coming in, uses up most or all of its energy to convert into shaft energy or mechanical energy, and then it exits or closer to ambient temperature back here. If we made a really efficient engine, then we might be something like this. Or a heat exchanger where we've got some ambient air pumped across like this, and we got a fluid that's passing through here. Starts out hot on this side, and some heat gets taken out of it, taken out of it, taken out of it, and it ends up over here. And the tube is the same temperature as the fluid going through it. Then we might see this kind of a distribution where it goes from some hot reservoir over here to some ambient reservoir over here. So this is a very typical type of setup we might see where one side of a part is hot, other side is close to room temperature. That could be a cross-flow heat exchanger or anything like that. So there's our delta T of X. Let's see how it works out in terms of the force that it generates. And we got fixed ends. So again, our total displacement equation is going to go to 0. paper, we'll scribble in here. So equation still applies like before. My U is going to be FL over AE, and then it's going to be plus alpha, and this time I've got integral delta T from 0 to L dx. All right. And in the fixed end case, we're still at 0 over here. So if I'm going to solve that for force, I got FL over AE on this side, and then over here I got minus of alpha integral 0 to L. And then my equation for what's inside there, I got that T naught out in front. That can come outside because it's a constant. And I got L minus X over L dx inside there. So I got minus alpha, that T naught, which was the delta T on this side. So I got a triangular distribution here. T naught on this side, 0 delta T on that side. So just a straight triangular distribution. So this one's going to be integral from 0 to L. It's basically 1 minus X over L if we want to break it into two pieces. So my force, I can bring the AE over L to this side. And then up front, I got minus alpha and T naught. I integrate up 1, it's just going to be X. And then I got a minus X squared over 2L. And that's going to be, if I do my limits, it's from 0 to L. So let's consolidate what we got here. Minus alpha AE T naught and over an L. And then inside the bracket, I've got going to be L minus L over 2. So just an L over 2 out here. And we'll see the L cancel. So the force that I have generated here, minus alpha AE, my delta T on the left side, the maximum one, and it's divided by 2. So there's what I've got to work with for my force. If I looked at it for the stress, which we've done before, just take it per area, minus alpha E T naught and over 2. Now remember, when we calculated on the previous example where we just had two fixed ends and a delta T, it was alpha times E times delta T with a minus. Here we got half as much as that, which should make sense for us because in the previous example, we had a delta T that was a constant value all the way across, same delta T across here. In my tapered temperature load like this, I had a T naught over here and I had 0 over here, right? The average delta T across there would then be, if I put this part of the triangle over there, I could get T naught over 2, which matches my alpha E times a constant delta T, right? If my had a constant delta T and it were this rectangle shape, if I take the top of that T naught triangle and flip it or hinge it over here, I could see I get half as much as I would for a full rectangle. I got a rectangle that's half as tall on delta T. The average delta T across here is half as much, and that's exactly what my formula is. And that force, even though it's expanding more on the left and less on the right, the force is going to hold constant all the way across. So we got a number that makes sense. It's a negative sign. We got alpha, we got E, we got the delta T in there. And because it tapers down, we saw it was half, which is right the value at the middle. All right. Which half of it is more delta T, half of it is less delta T. So overall, that's what we should come up with. All right, anybody had any questions about that one where we looked at a tapering delta T? Only difference is this part. The FL over AE still stays the same as it. All right, I'm gonna gloss over this one for lack of scratch paper right now and jump over and talk about a couple of special cases. So zero stress members, there are two ways that we can end up with zero stress members. One of them we already talked about was having one or both ends free, right? Don't have any supports on either end in the axial direction, or we don't have it on one end, it's free, then we can't build up any force inside it. So that means zero force and zero stress. The other possibility that we can have, even if we have fixed supports, is if this integral from 0 to L of epsilon equals 0. And if we take alpha out of there, essentially that means if my integral for delta t along the length is a total of 0, then we're also not going to build up any force. So let's say we have an integral or a distribution of the load that's something like this. I've got a hot reservoir on this side, and I've got a cold reservoir on this side. So some sort of a Carnot or very ideal type engine. And I've got hot reservoir here, cold reservoir here, and something flowing across here. So this side of the beam is heated up, and this side of the beam is cooled down by the same delta amount. So here's my delta T distribution. Goes from somewhere hot on this side above my ambient to the same amount below my ambient over here. So I have that same linear distribution, but instead of all of it heating up, some of it's heated up, some of it's cool. So the left side of this beam, to varying extents, is going to be expanding. And then at the same time, the right side of my beam, to varying extents, is going to be compressed in. And since this is a positive area and this is a minus area, if I integrate across here, I get this triangle minus this triangle, or 0. So however much this one stretched by on the side, it shrank by the same amount over here. If you have a case like that, then we can have zero stress even with the ends fixed. Now, in reality, we're very unlikely to come to this exact case, but there are plenty of times where we might be flowing from a hot reservoir to a cold reservoir in an HVAC or refrigeration cycle or cryogenic cycle or anything like that, where we could take some advantage and say, okay, while this part of it's going to be expanding, this part's going to be compressing, and we can reduce the overall stress. Even if this isn't the exact same, maybe it goes from more hot to less cold, I'm still taking away from the amount of force that's generated in that part. So hot to cold reservoirs do us a favor in terms of either zeroing out if it's really good, or at the very least, we're lowering the amount of stress because this integral gets smaller when we have some positive and some negative balancing each other out. All right, did anybody have any questions about the basic thermal expansion? How we set it up? It's always the same on strain, alpha delta T. And then how we go up to displacement, whether it's constant or a function for delta T. All right, that's a good stopping point. Let's break and come back at 10 after. I'll go get some more scratch paper, and we'll And we're back. So let's take a quick look over at the summary slides. This will just give us a rundown of everything that we went over. So thermal expansion, we got those strains in all three normal directions. We got our basic definition here. Total strain, mechanical plus thermal. So here's our expression for that. If we integrate that over the length of the bar, we get sigma times L over E, or FL over AE on the mechanical side. And then on the thermal side, we get alpha and integral delta T dx. If we have a constant delta T like we did in the early examples, we can just make that delta T times L and get this expression right. So for an axial bar, we've got all of our basic expressions right there. Some special cases, free ends, we're going to have no force or stress. That means all of our strain is going to be in the thermal aspect, and it'll be free to expand by this much. For fixed ends, we assume no displacement, meaning also no total strain. And that means that the mechanical and thermal strains have to balance each other off, plus and minus. Here's my expression for the stress. If it's a distribution, or if we got a constant delta T, it's going to be E alpha delta T and a minus sign. And between force and stress, we just multiply by area to get our force expression. Let's say we have a case where we have both some mechanical load and we have a thermal expansion applied. Well, if it's got one end and the other end has some load in it, P, epsilon XX can be P over AE plus alpha delta T. And then my displacement is going to be something like this. So if I have both a thermal expansion and a applied mechanical load, I'm just going to add those two effects together. And then we got the one that we've tried several variations of, a two-bar parallel system. Big boundary condition for that one, U1 equals U2. If they're by themselves and there's no external force applied, then F1 plus F2 equals 0. I've also got it set up here. If we had some external load plus temperature changes, then there's going to be our force balance. All right. So we use P if there's an external load. If not, then it's 0 equals F1 plus F2, or they have to be equal and opposite when they're by themselves. So there's all our thermal expansion goodies right there. Next thing we're going to talk about is Euler-Bernoulli buckling, and then we'll throw that together with thermal expansion here. So if we look at an ideal pin-ended column, all right, so we're going to consider pin-type support on both ends and also free to move in the axial direction. Okay, so as far as the beam's concerned, it's simply supported, and then we can push down and cause axial deflections. So we're going to assume it's a straight bar, linear elastic material, and it's free to rotate on the ends about some frictionless pins. We're going to be symmetric in that XY plane, and we're going to keep our deflections within the plane of the page. So we load it with some compressive force P pushing through those pins on the end there, right? So if this were ideal and there were no perturbations or imperfections in the beam, we just push down on it. It should just compress in that axial direction. But we don't really have anything supporting it from bowing out in one direction or the other with those pinned ends. So if I push up to some certain critical load, it should just compress like an axial bar. Once we exceed some critical load, which is a function of how skinny this beam is, how flexible it is, and some other factors, it's prone to, at the slightest little disturbance, like a stiff breeze, or maybe there's a few less atoms on this side and a few more on this side, it's going to be prone to moving out of plane from one side or the other, off its parallel direction. So right at that critical load, the beam is going to bow out. And for a simply supported case, we should get a nice smiley face or frowny face shape just like this. And that means we're going to have some displacement V of X along its. Now, because all of that force that we're pushing down is axial, we're still going to assume that our reaction down here is an equal and opposite axial load. And although I have a pin that controls transverse deflection here and here, it should just be a little bit of stability type force. So we're not going to have much in the way of transverse forces on this. That means we're going to be in a pure bending case like we derived the beam theory from. So in that pure bending case, we don't have any transverse force. We won't have a V of X on there. And we got P pushing on both ends. If I take a slice through this anywhere along the inside of the beam, I cut it, I'm going to have some bending moment, right? And then if I've got X this way and Y this way, my Z is going to be this way. So my moment with my right hand rule for Z is going to be like that. And then I've got two compressive forces pushing all the way through the beam. Remember, that beam's still going to carry in the axial direction P all the way through compressive. Only now this P is offset by however much it displaced out, that V right there. So right here, I can see I've got a balance of forces, P going up and down. And then these two P's are offset. So they're going to create a force couple. As drawn, that would go counterclockwise, right? So P times V gives me a counterclockwise moment, as does my internal moment, M of X. So there's my summation of moments balance. I can see that it's going to go against my sign convention. M of X is going to have to go clockwise by P times the displacement at any given location in there. So that means down here, where I don't have any displacement, my moment should also be 0. And that makes sense because I got a pin in. My moment's going to get bigger and bigger the farther this deflects. So toward the center of that beam, I should get my max moment. And then it'll come back to 0 at the top. And then remember also from our beam chapter, moment equals EI times second derivative of deflection. So I can put that in for M of X right here. And if I put them on the same side, EI V double prime, there's M of X plus P times V equals 0, right? What we had from our summation of moments, but we're substituting the beam bending theory, EI second derivative of V. And if we move the EI down to the bottom, because 0 on this side, we've got V double prime plus P over EI times V of X equal to 0. So we've got a second order differential equation there. It is of a classic closed form solution. Second derivative plus some constant lambda squared times the function itself equals 0. And there that lambda squared P over EI. We can have a solution that is always good for this equation, C1 sine lambda x plus C2 cosine lambda x. And no matter what we have for our constants in there, we can always take two derivatives of this and add it with that, and it's going to come out to 0. That makes sense because if I go down two derivatives, I know I'll get back to a negative of sine here. I go down two derivatives, I'll get a negative of cosine here, and there'll be a lambda squared in front, which is already in front of this. So I got, on this one, I've got lambda squared times a negative for this one and a negative for this one. And here I've got lambda squared in front times the original stuff. So that definitely always goes to 0, right? Closed form solution. Now, boundary conditions. This is our general equation right here, V of X, all right? There's two boundary conditions that we have to work with, all right? Maybe let's go back to the main page here, all right? So over here, one boundary condition I have is that V at 0 has to be 0. We're pinned down at that end, so we're not going to move in the transverse direction down there. And also, V at L has to equal 0 as well, because I've got that other pin joint up at the top. Now, let's look at this bottom one, because this is going to make our equation twice as simple for us. If I'm at 0, sine of 0 is always 0, right? So that goes away. So V at 0, if I'm trying out this down here, And bear with me so I don't have to jump off to the chalkboard. V at 0, sine of 0 is automatically 0. So this whole term's going to go away, right? But cosine of 0 is 1. So I'm going to have C2 still there. All right. V at x equals 0 has to equal a total of 0. So what do I know about C2? C2's got to be 0, right? Because for V at 0 to equal 0, C1 can be anything, and the sine term is going to go away, but the cosine term is still going to be. So that means that to make this function work, I can't have a cosine term because cosine doesn't equal 0 at the start. All right. And if I look back here and just make my best guess, I see starting at 0, that's like a half of a sine period, right? That's a sinusoidal type shape. Goes from 0 up to some max at L over 2, which would be like pi over 4, and then at pi over 2, it would pass back through 0. So I could see a half of a sine period shape, right? My sine curve would go something like this, right? And I could see I've got half of a sine period basically right there. Now, my other boundary condition is that V at L has to equal 0, all right? And there's more scribbling than I care to do, so let's jump over. So we've already gotten that V of x is going to be C1 sine lambda x, right? We took away the cosine part. All right, so this is our thing. And our second boundary condition that we have to work with is that V at L equals 0 also. That's going to be C1 times sine of lambda L. Now, that means either C1 has to be 0 or sine lambda L has to be 0. If C1 is 0, we don't have any deflection, so that's kind of the trivial solution. So the other option is sine lambda L needs to go to 0, right? Because we can't have no deflection or we won't have a shape, right? So 0 needs to equal sine of lambda L. This is the non-trivial solution, all right? And we know that sine is good at 0, it's 0. At pi over 2, it's 0. At pi, it's 0, and so on and so forth. All right. So that means lambda L needs to equal some multiple of pi over 2. Pi. I see you guys are catching me at the end of the day. That's good because I slip a little bit too at this hour. 2 pi for a whole period, right? So pi, some multiple of pi, our sine curve always passes through 0. It goes back and forth at 0, at pi, at 2 pi, at 3 pi, etc. Okay. So lambda L needs to equal some multiple of pi. So that means V of x is going to be C1 sine of this setup right here. So lambda then needs to be some multiple of pi over L. So some number pi over L times x, some multiple or integer there, either pi or 2 pi or 3 pi or etc. And then when x equals L, if this is some multiple pi, then this will 0 out. So here's our displacement function. Note we don't know how much it displaces by. The magnitude is still hanging out there as a unknown. But we need the shape is the important. So I got n pi x over L there. That means my critical load to cause buckling, remember this is lambda times x right here. And we said that lambda squared was P over EI. So lambda squared was P over EI. That came from our substitution for the differential equation. And that tells me n pi over L squared quantity needs to equal this. So I can solve that right there. I see the N, the pi, and the L all got squared. Multiply it by EI, and here's my P critical for buckling for certain mode. Okay. Now the first one, where N equals 1 is an integer, that's going to give me my simple buckling shape. Half of a sine period, and I push with pi squared EI over L squared, and that's when it's going to pop out. I don't know how far it's going to go, but I do know it's going to pop out into this sinusoidal half period. If I instantly push with 4 times as much load, I get to the second buckling load. If I put in 2 here, I get 4 times that original one. And if I manage to push fast enough that it doesn't trip out here, and I go straight to 4 times that critical load, I'll get a full period, a full sine shape. So I can see my first buckling there. There's my second buckling mode. Unless I'm really instantaneous with that load, I'm never going to get to P2 before it buckles in the first mode shape. So this is going to be what we have. If we happen to have a support here or something that restrains the displacement, then we can pop it into our second mode there or other higher mode. But pi squared EI over L squared, that's going to be my buckling load for a simply supported shape. And we got that all from our beam bending theory. So there's our smallest load that buckling will occur. Notice that as the material gets stiffer, buckling load goes up. As the moment of inertia goes up, that's how beefy is our cross section, also means it's more difficult to bend it out of linear. So that goes up. And then as the length gets longer, my P critical goes down. All right. So no matter how beefy I make the cross section, if it's a 1 by 1 foot full-size I-beam, and it's only 1 foot tall, it's almost impossible to buckle, right? Because I have huge numbers for this and small number for that. If I make that 200,000 feet tall up to space, even a 1 foot wide I-beam is very wobbly at that length, right? And I can see that represented here. E and I count as a linear increase for the buckling load, but length causes the buckling to go down at a square rate, right? So length is the most important term in there, with E and I being linear importance and L being a square importance. L makes the buckling load go down. It's easier to pop it out of plane, and E and I go up. We also have to be careful in a 3D situation. If I'm pushing down on an I-beam like this, then I could buckle about either one of these axes, right? So in this case, if it's a really high moment of inertia about Y and a smaller moment, an H-beam has a smaller moment than an I-beam this way. So it's going to buckle using that H-shaped cross-section. It'll buckle off from the Z-axis instead of off from the Y-axis. So in a 3D case, if it's not constrained with a pin through there, it's more like a ball and socket joint, then it's going to buckle to the left or right before it would buckle up or down in a case like that. So in a 3D case, you have to be careful if it's not the same cross section looking on both axes. One other thing to note is that the yield strength or the ultimate strength does not affect buckling as long as we stay elastic. So if the beam is long enough, we're going to get to the buckling load and stress before we yield the material, right? That will be the case of the 1 foot beam that goes all the way up to space. We'll definitely buckle that before we yield the material. If that same 1 foot by 1 foot I-beam is only 1 foot tall, we're going to have to push really, really high to get the buckling to occur because the length is so short. Then we're going to fail the part by general yielding. So we can check and see whether the general yield happens first or the buckling load and buckling stress happens first. Whichever one is lower is what's going to happen first. Now that takes care of the pin-pin connection, but there's also some other cases we might consider. What if we have no rotation at either? Or let's say we have one end's fixed and one end that's free to rotate, so a pin fixed type connection. What we want to look for is this same characteristic length, right? And that's from no moment to no moment or no curvature to no curvature. Remember, moment EIV double prime. So let's try this one first, all right? A fixed, as we've seen in some of our transverse loading beam cases, a fixed end is going to bow into a cosine type shape, or more specifically, a 1 minus cosine type shape, but a cosine type period like this, all right? Now, in that sinusoidal shape that we looked at, we had the same curvature, let's call it a smiley face to the right, all the way through. And since I'm pinned there and there, I got no moment. Well, I got definitely a moment here and a moment on this end because it's fixed and I see some frowny face curvature, but then it goes to smiley face, then it goes back to frowny face. So where that curvature goes to 0 is the same as where these two, the curvature and moment went to 0. That's my characteristic length. So if I pick out something that looks like the left side on this one, it's going to be from the quarter point to the 3/4. So my characteristic length for this one is going to be half of the overall beam length. That's called our L effective. And this is what we're going to put in the bottom of our equation. So that means here with L effective at half L, it's 4 times as hard. Got to push with 4 times as much force to buckle this one as we do the one on the left. Maybe another one that's not too tough to think about is a fixed free case. All right. I've got a fixed end here, so my max moment and curvature. And then on the free end, I don't have any curvature. So here's my 0 moment and curvature point. This is maxed. In order to find another 0 point, I've got to mirror this image down to another 0 point here. So one that's fixed on one end and no support on the top, no transverse support, is going to give me an effective length of 2L. So it's actually 4 times easier to buckle this free fixed condition as it is the pin case. So case C, 4 times more load. Case D is 4 times less load. And then for the fixed free, we have to do some kind of math to figure that one out. But I know on the fixed end, I'm going to have some moment. It's going to have to turn the other direction at some point. And then the pinned end over here is going to have 0. So 0. And then wherever my inflection point works out to be, with the math, it approximately is about 70% of the length. I can find that 0 curvature to 0 curvature. So there's my B, C, and D are just offshoots. I can take the same formula I used here, but plug in a different L on the bottom. And that'll give me my buckling load for different kinds of cases. All right. So there's all my basic cases. In our summary slides over here, I've got those set up. There's our basic buckling formula and what we plug in for L effective for the other 3 bookend cases. Now let's think about buckling in terms of thermal expansion. So we know that the buckling load is the buckling load, pi squared EI over L effective squared, and that is not dependent on temperature. It's only dependent on the material, the cross section. So the geometry and the material are what controls the buckling load. It doesn't matter what creates the buckling load, whether that's a mechanical or thermal driven load. So let's consider thermal buckling where we have fixed or pinned ends, no expansion. So my overall displacement is going to be at 0. And I've got my same thermal expansion formula, FL over AE plus alpha integral delta T equal to 0. So if we got 2 fixed ends or 2 pinned ends where we can't move them, and we always buckle at P critical compressive. So my axial force being a tensile positive, I say F equals minus P critical and just throw it in there. And then I can solve. So my expression, if I got a constant delta T along the length, I can solve for the delta T that will cause buckling. It's going to be P critical over AE times alpha. Note we came up with a positive number for delta T. That's what we expect to get, because when we heat it up, it wants to expand. By pushing back on it and keeping it the same length, we are compressing it, and that's when it can buckle. So we cannot buckle anything that we're cooling down, because it would want to shrink. It's going to be a tension. It's very, very hard to buckle something in tension. I saw it done once, but I wouldn't recommend it. So we can see that a positive delta T gives us, or is what we get when we have P critical as compressive load and AE in and out. So a positive delta T will give us, we'll get our solution from a given buckling. If we substitute in for some of those other parameters in P critical, we can calculate that separate from anything thermal, and it's always P critical. But if we throw these in, we get pi squared I and alpha A and L effective down on the bottoms. Axial stress at buckling is always minus P critical over area, no matter how we get that buckling load P critical. And this is important because if we're checking to see whether it's going to buckle or yield first, we need to compare this number with the yield stress. So this is our critical buckling temperature. Note P critical is its own formula. We can solve it without any temperature thought, and then AE and alpha going on the bottom. So this formula is good when neither end is able to move. Let's take a look at a quick example here. And this is a very typical one that we might come across in terms of buckling and thermal expansion, is a pipe with two flanged ends and then two fixed supports. So I can see I got a bolt pattern all the way around. That means I'm not going to be able to rotate this about any bending plane, either the one out of the page or the vertical one. So we've definitely got a fixed type end condition. And then we've got our length, we've got our pipe diameter, we got our thickness, so we can figure out everything that we need for that one. Got our modulus, and then we got our material property. So let's sketch it out and see what we come up with here. All right, I got a fixed case, flanged ends, so no rotation allowed. And I've got my L and I've got all my properties. So my displacement, FL over AE plus alpha delta T L, has to equal 0. And I also know that my force needs to equal minus P critical. So that one throws in there. And I can solve for my delta T critical, the one that's going to cause buckling. It's going to be the same as we had on the previous page. Going to be P critical over AE and alpha. So there's our equation. For area, I can just take pi over 4 d outer squared minus pi over 4 d inner squared, and I got the thickness and I got the diameter, so I can get that. Okay. For my E, I just got the material property. For I, bending moment, I've got power 4 and then another, can be pi over 64 d outer to the 4th minus pi over 64 d inner to the 4th. Remember, it's pi over 4 r to the 4th, or if we're keeping it in diameters. So I can get my I. That's just a function of the geometry. So we've got E, we've got A, we've got alpha, and then P critical. P critical is going to be based on our end conditions. Pi squared EI, so we got those. And then it's over L effective squared. All right. Our length for this pipe was going to be that 8-meter distance. And I can see that on a fixed case, I get a cosine type shape, 1 minus cosine type shape. My L effective then is going to be half of L from one inflection point to the other. So I got my L effective as well. All right. So L effective is going to be 0.5 times L, which is going to give me 4 meters. And then for my other portions, that's all just crunching numbers. I'm not going to make us go through those too much. We can just plug and chug to get them. But I's just a function for us there of the values. I'll grab you the number here. Second. Here we go. All right, so D outer, D inner. If we crunch this little calculation, we should get 2.46 times 10 to the negative 6 if we're in meters to the fourth. All right, our area is going to crunch out at 0.0023 meters squared. So we've got A, we've got I, we're given E, and we plug and chug. Peak critical then is going to come out at 288 and some change kilonewtons, or 288 times 10 to the third. Got that too. And then my delta T critical that's going to cause this to buckle will only come out to 38 degrees change in Celsius. That's a fairly long pipe, 8 meters, 24, 25 feet long, ballpark. And not too large around. So we can see it doesn't take a lot of tilt to temperature. That's going to be maybe 70 or 75 delta Fahrenheit. So if we have like a steam line or something like that, or anything that's at a higher temperature, we're definitely in a position where we could buckle it fairly quickly. All right, so we evaluate the end conditions. Those affect two things. In the axial direction, they set us up for 0 overall displacement. And then the fact that they're no rotation, fixed, that gives us our L effective. And that's everything that we need to work with there. We can plug and chug from that point. All right, so that covers everything that we need to know about buckling. There's our buckling information. And then here on the last slide of our summary set, we know thermal buckling is going to occur just like any other buckling occurs at compressive peak critical. So F, which is our axial force tension positive, F equals minus P critical. We plug it in right here. And if we have a case where there's no axial movement allowed, then we could set U equal to 0 in our mechanical plus thermal and solve for P critical right. Okay. This formula is also just as good if we have a non-zero displacement. Right? Still going to be minus P critical for force, L over AE and alpha delta T, or constant alpha delta TL. But this we could use for something like a 2-bar linkage, right? In a 2-bar linkage, instead of U equals 0, we have U1 equals U2. And for the buckling one, we know the load is going to be minus P critical. We also know for the other one, we get tensile of this same number because forces have to be equal and opposite, right? So this works for non-zero as well. It works for 2-bar linkage. The one that's going to be buckling, we have to assign that compressive P critical, and the other one would get a tensile of the same value. But we can crunch through and figure out what delta T will cause that. And then our axial stress at buckling, just minus P critical over A. That's important when we want to see, is it going to buckle first or is it going to yield first? Whichever number lower is what will happen. All right, anybody have any questions about that last bit of material that we looked at? Let's go over our last couple homework problems. We had 3 left that had to do with thermal expansion. Okay. So here we got an expansion joint that we install in that exhaust duct, the same one that's been having problems in problem number 2 and the torsion homework and et cetera, et cetera. And this we might have also heard called a bellows. It's a giant spring basically, and it's formed from a single rippled piece of material, usually welded around, and it's designed to act like a spring so that instead of having 0 displacement where we really build up those stresses, we can let this pipe expand a little bit and still have some force in there, but much, much less. And because it's all one piece and airtight, we don't get any leakage of the exhaust. So our duct here, we're going to say is 18 feet, and then the remaining 2 feet there is going to be the bellows. So we got EA and alpha for our part right here. Since this is an exhaust duct, we're going to say it goes from 800 degrees delta T to 600 here. We're losing a little bit even though it's insulated. So we got a tapered delta T. And this is how we should think about it, okay? We've got a bar and a spring end to end, okay? Well, if I set up the displacement for the spring to go up, and I push F spring this way, F spring equals K times U. So I've got that expression right there. Or U for the spring is F over K. So this is really no different than a two-bar linkage, whether you think about them end to end or whether you think about them next to each other. It does the same thing, okay? So we can make this just an offshoot of our two-bar. U for the bar, which is going to be FL over AE plus my alpha integral delta T, is also going to equal U for the spring, which is just F over K. And because they're end to end, if I take a little cut right here, as drawn, I have F pushing up into the spring. So if I were to draw these two as a free body, and then here's my joint, and then here's my bar, F for the bar goes this way, F for the spring as drawn goes this way. So forces are also equal and opposite, just like if I were to grab them side by side. Okay, so we're still going to have F bar and F spring be equal and opposite. And we're going to have our regular formula for U bar, and our U spring is just going to be F over K. So a two bar, but one side is going to be F spring over K. The other side is going to be everything usual for an axial bar with thermal expansion. And the forces will still be equal and opposite. So solve for the force in the bar and the stress, and then the displacement at the end of the duct. So this one's free to expand some certain amount, figure out how much that is. We can either do F spring over K, that's the quick way, or we can do F bar L over AE plus the alpha delta T. They should come out the same, but we'll calculate that force by equating the two displacements, just like with any other two bar. All right, so it's just a two bar linkage. Now for problem number 7, first thing in the morning, we take a wing off a Harrier and we stick it onto this fixture here. So we can go take it off somewhere else, take it to the paint shop, maybe get it reworked and machined, and same thing for the fuselage. Well, we did that at 6 a.m. down at Cherry Point where it was a little bit cooler, not super cool, but we roll it outside, and in the afternoon the sun comes up, and after we get back from Smithfields and we've had all that vinegar barbecue and hush puppies and we're kind of lethargic, and we go to try to move this thing and take the wing off, it doesn't come off, it's stuck. Well, while we were out to lunch and all through the morning, the sun heated up the wing to 130 degrees. We started at 70 in the morning. The fixture was still heated up by that muggy ambient air at 100 degrees, but it's shaded, so it doesn't get the direct solar heating. So it's going to have a different delta T on the bottom. All right. So we heat it up by 60 degrees. We heat it up by 30 degrees on the fixture underneath it. So I got two different delta T's and also two different alphas. The wing's aluminum and the fixture's made of steel. True story, this actually happened. And we've got all our properties for each one. So set up a two-bar linkage. This is just a two-bar linkage. They're held together by some fasteners and they're stuck together. So figure out what the force in each one is, what's the stress in each one, and then the expansion of the system, which is one or the other. They should be the same. So that one gives us a chance to try a two-bar linkage with different delta T's. And then our last problem, we're going to think about an aircraft like a V-22 or F-35. When the engine is pointed in that vertical direction, some of the exhaust comes down and heats up the deck. And we're going to say that all happens right between two stiffeners here. So in one panel width. All right. These stiffeners are pretty good against bending. It's not going to let it move up or down, or it's certainly not side to side with that continuous deck. But T-beams are all pretty close to the centroid. So they're not super strong in torsion. So we're going to treat these like pin stiffeners. They're easy to rotate, but they're very hard to displace. So they'd act like a pin type joint. So that means between these stiffeners, we can pop up or pop down like this as the material wants to expand. So we can pick out a characteristic shape for that one. And we've got our dimensions for the deck right here. We got our length, and then we got our cross-section dimensions. And then we've got a distribution for the temperature, hottest at the center of the exhaust plume and then tapering down to no delta T on the sides. So we can set this one up for a 0 total displacement. We've got our delta T of X. And it's some max delta T naught in the middle, and then it tapers off to 0 with this quadratic. So we want to solve for what delta T in the center there will cause this section of the flight deck to buckle. So figure out that delta T, then we get the force and the thermal stress at buckling. And then we've got that problem. So you can try one with a non-uniform temperature, a 2-bar with different temperatures, and then a 2-bar where we're only looking at the thermal on one side and we've just got simple spring formula. And so keep chugging along. For those of you needing that alternate review time and earlier exam, we'll get that set up. And then otherwise, Wednesday, we'll be looking at some fleet issues. Nothing heavy on the brain. We'll just come in and relax and talk about stuff. And that'll be on Teams for those of you out in TV land. I'll send you a separate link for you. Then Monday, we've got our review of this homework. So we got a whole week to work on that. All the material we need is finished. And then next Wednesday, our exam. Anybody have any other questions or whatnot?
Will
So
Wednesday's lecture be recorded if it's on Teams?
yeah, I will still be able to record it because Teams has its own recording thing. So I'll still put that in the OneDrive location. We'll just be on a different application for the broadcast.
Thank you.
Yep.
Sir, when will we be getting our grades back?
I still have 1 or 2 stragglers on that one, but should be before next class. On that note, also, if you happen to be one of the few people that still has homeworks hanging around, it's not a problem to get them in. Just make sure we have them. I need everything to be 30 out of 30 by the end of the semester. Okay. Most of you have gotten your stuff in, but there's a few stragglers here and there. So just keep working on those. It's not too late to turn them in. I'm not going to click in there and show who it is, but just so you're aware.
That was big, quarterly.